Right, so welcome to the practice session. So there are a couple of things that I want to do in this session. Firstly, I would like to get some protein structures, but there is a slight complication with the protein structures that we're going to work with. And that slight complication means that we have to use the cluster. Am I not recording? Now I am recording, so I have got this. I have got recording on the go. Okay. So please, there is a slight complication with the protein structures, and I'll just show you how to deal with it. Fortunately, we've got the cluster, and the cluster can help us resolve this huge issue with the proteins that we have that we need to sort out before we can use them. Okay. The problem is that the proteins we're going to work with have multiple conformations. And so we're going to have to worry about it. So there's more than one conformation saved in a single file. And that causes problems with the docking because then there's an overlap of the conformations. You've got the same atom listed twice. And then the software worries that there is an overlap with the system. But we can easily sort it out. But if you have a look at the tasks that I've given you, the continuous assessment task, you'll see that there are some structures that I've asked you to look at. And so I'm going to have a look at one of them. There's 5-REC. And I'm just going to search for 5-REC and see if I can find it. So you see I'm on rcsb.org. Just go to rcsb.org and you can search and you'll find 5-REC. Right. So please, when you do your continuous assessment, it gets marked by me, and it also gets marked by an external examiner as well. And so we can't just have a list of results in it. We're going to need a little bit of an introduction. So you need a bit of a justification for the project, and the project that you're doing is you're looking at how molecules interact with the SARS-CoV-2, the COVID-19 main protease. And so it's quite interesting that on RCSB, some of them will, this is to be published, but some of them do have, they do have some references. So please maybe just do a short introduction with the background to SARS-CoV-2, and maybe if you can find a little bit of information about this main protease, that will be really nice in an introduction, because if we can inhibit this main protease, surely that is going to be a way for managing the disease itself. So as medicinal chemists, it'd be nice if we can find small molecules that inhibit the main protease. Okay. But when you go into 5-REC, here it is. There's a lot of information. I'd like you to go straight to the download files. And the format that's easiest for us to work with is the PDB format. I've been saying it again and again that MOL2 and PDB are really nice to work with. So please go to the PDB format and download it and just save that file. Okay, and that now should be saved in downloads. Okay. Right, now there are problems. I told you there are problems with this, and those problems can be sorted out quite easily on the cluster. So I'm going to just copy that to the cluster before I do anything. Go to Carbon. If you don't have a login to Carbon, drop me an email. And I will create that login for you. Okay. Make sure you have a login to Carbon. Okay. So I need to go to downloads, and it's 5rec.pdb. Okay. Now there are two conformations in that. There are two conformations that are in that particular file. And so I'm going to need to use the power of a cluster to just, or the power of at least of the login node. Here we go. Right. So if I do ls, I've now got quite a bit of a mess here. But maybe if I do ls just star.pdb, it'll just show me, and I can see exactly, here's the protein structure that I've got from the PDB. But the problem with it is that it contains two conformations. So what we need to do is we need the Autodoc tools that's available on the cluster. And so if you do module add, and you type Autodoc, by the time you type AU, you can use tab completion to get it. So if you type AU and then press tab, you don't have to type all of Autodoc. And it's MGL tools. So if you type then an MG and press tab, it will automatically complete it for you. This.
Prof, I have a question.
Yes, what is your question?
I just want to know, how do you know that the protein has two conformation, and
one way to try is to take it and open it in Autodoc tools, like we opened the ligand yesterday, but open it using the main menu, and then try and save it. And then this poor software doesn't know what to do. You'll get a lot of errors coming through. So you will find that there is a problem. And when you actually try to save the protein at the end. So Autodoc tools can't handle all of those conformations. So we can just do a quick fix now. So if you add these here, module add Autodoc MGL tools, then what we can do is we can now, and I've got this in your lecture slides. If you look carefully in the lecture slides, there is a prepare. So what you do is, okay, let me just get it back. So it's prepare, and it's underscore, it's a long word, so prepare PDB. But when we've got enough of the letters that it knows where it becomes unique on the system, pressing the tab key will then type the rest of the word for us. So if you type prepare underscore PDB, there's only one thing on the cluster that has prepare underscore PDB start, and it's this long script that's over there. And then what you do is you do -R, and then you do 5 rec.pdb. This is our problem PDB. So you do prepare PDB split alt conformations -R 5 rec.pdb. And what happens? It returns, it says returning two conformations, the A and the B conformation. Now let me go to WinSCP and just refresh and see if there have been any changes on my system. And yes, there have. You can see that was my original one that I downloaded. That's the PDB structure that I downloaded. And it's split it into an A conformation and a B conformation. If you really have a lot of time on your hands, as I'm sure you do, I'm joking here, I know you don't have a lot of time on your hands, you could try both. But really, we only just really need one of these. So I'm going to go into documents, and I'm going to copy the A conformation here. I'm not even going to worry with the other one. If we had time, I would do both of them. But I think time is short. We want to move as far as we can. And so I've now got the A conformation is now available. Okay. Now Autodoc tools will be fine with that. And so if I can find Autodoc tools on my system, I've now split it, and now I have a single conformation. And so I won't have trouble working on this. Okay. So first thing we do is file, um, uh, preference is set. File preferences set. Remember that we need to set its directory, and the directory, its documents is where I want to make it. So I'm just going to make this nonsense over here. And when you try and set it, it will complain. And then you will be given the option to find the folder you want. It's documents I want. So please always set it to being a particular folder, and that particular folder will contain, that's where you're going to save everything and have it run from. Okay. Right now, when we open the molecule, we're going to file read molecule, and it's that A confirmation. We've got it there. It'll open up really nicely. We've got it there. If I'm not sure you can see it, but can you see those red dots around it? Can you see the red dots? Those there are the water molecules. Okay, remember that in crystal structure it might not show the hydrogens. Hydrogens are not seen in crystal structures, and they might be added on afterwards. In this case, they're not added on, so there are no hydrogens on those. So those dots are just the oxygens of water. But what I'm going to do is first thing is I'm going to get rid of those waters. I'm going to edit and delete water, and it's gone. Okay, that's the first thing. If you look very carefully, can you see an isolated molecule down here with a sulfur, 2 carbons, and oxygen? That's dimethyl sulfoxide. Often dimethyl sulfoxide is used to dissolve ligands. So I wonder if that's where it's come from in this crystal structure. But its code, if you look down, you'll see there are 4 of these DMSs. So I'm just going to select them, the DMS. There are 4 of them. So I've selected all 4. You can see there are 4 yellow DMSs that are selected. And I'm just going to edit, and I'm going to delete this, delete the selected atoms. And so now, warning, yes, I'm happy to continue. And now we've got the DMS is removed. Okay. So now what we have is the protein, that's COVID-19 main protease here, with a ligand bound to it. And what we need to do is we need to identify the ligand, and we also need to save it safely and remove it so that there's space for whatever we want to place in the active site of this particular protein. And we can see here, this T1J is not an amino acid code. You can see this one here. If I select it, you can see it's over there. That there is the ligand, but maybe I can use one of these other buttons to highlight it. And you can see over there, you can see that there is the ligand that is co-crystallized with the protein. So if we were to take the same compound and redock, we would hope that it would appear in exactly this orientation at exactly this place in the protein if we got the docking working well. Okay, so that would be very interesting to see if we can get that to work. Okay, but what we need to do is we need to save that as a reference. So if you just select it, make sure it's selected, and then you can go File, Save, and Write PDB. And I'm going to then call it, you're going to have to dig through this top line here. I'm going to call it 5. I don't want to say if it's a protein, I just want to say it's a co-crystallized ligand. Done. Okay, and so then it's saved. If I go to my computer, if I go to my documents, and there it is there, and I open it with Notepad++, you can see all the atoms in the co-crystallized ligand. But of course, we can see that my guess for an active site that I did in the lectures is not too bad. That the x-coordinate of this co-crystallized ligand is centered around 23. The y is centered maybe around 15. And the z is maybe centered around 4.5. That will be a really nice place to set the active site and to when we do molecular docking, we can then try and go for that active site. Okay. Right, so now I've saved that. It is safe. This co-crystallized ligand is safe. It's in its own spot. And so I don't need it anymore. I need to make sure it's removed. And so I'm going to edit and I'm going to delete, and I'm going to delete those selected atoms as well. And now you can see the area that it occupied is now safe, is now clear. And so if we were to redock it back, there's nothing in the way for us to dock another molecule to this particular protein. Okay. So what we've done is we've removed all extraneous molecules from this. We've got a reference for where the active site is, so that is fine. Now we just need to get this protein cleaned up for work with molecular docking. And so there's some things we have to do. And so one thing that I notice is it's missing hydrogens, but I would prefer only hydrogens that are available for hydrogen bonding to be present on this. And so if you go edit hydrogens and you add, okay, I could have done a shortcut, but I'm intentionally doing it the long way around. You'll see that all of the hydrogens are now, I hope you can see that. There's a difference now, and you can see the little white lines for the hydrogens on that. And there are too many hydrogens now because you will see there CHs as well, which are not important when it comes to the molecular docking. And they cause, so it's best to remove those. And so what you can do with hydrogens is the second thing you can do is you can merge nonpolar hydrogens. And so that'll take away hydrogens we don't need in the calculation and leave only the hydrogens that we do need in this calculation. And you'll see the OHs remain, the NHs remain, and so those are present, remain present in our system. Okay, so we've dealt with hydrogens. A couple of other things we have to do is it would be nice in terms of electrostatic term. Remember molecular mechanics, we have that electrostatic term. In docking, there's a similar term for electrostatics, but of course, we need to know the charges on all atoms to be able to work that. And so what I'm going to do is I'm just going to quickly compute gas-to-get charges on the system. And you see that it's added, the total charge on this protein is -3, and it's added charges to every single atom. So if I were to save this, we would be able to look in the file and we'd be able to find the exact charge on every single atom in this file. A final thing that we need to do is we need to assign atom types, and that is so that the program knows exactly what each type of atom is. Is the carbon an aliphatic carbon? Is it an aromatic carbon? It needs to know all of that information. Is it an oxygen that's open to hydrogen bonding? And what type of hydrogen bonding is it available to? So let's go and you go edit atoms and you assign an AD4, an autodock4 type, AD4 type. Okay. And so now this protein is now totally ready now for the docking process. And so what I'm going to do is I'm going to save it. And now, instead of writing a PDB, I want to write a PDBQT. I'm not sure if the Q stands for charges and the T for torsions, but I think it does. But we need information. We need a lot of information to be recorded in that file. So write it as a PDBQT file. And the default is often fine. You see, if you go to the end, it's given the name with a PDBQT extension. And we've got that. I'll have to just troubleshoot that. So my apologies. I will see what that is. But this is the, okay, I just need to see what that issue is. This is the type of issue you will get if there are multiple confirmations on the system. Okay, so this is the procedure you're going to follow. And so let's just see and save, and let's see if it will allow me to write a PDB, just a PDB. I'll give it a different name, but I'll troubleshoot that and I'll give you the information that we need. I normally work this under Linux, and Linux has worked fine. Okay. Okay, so what I might do is I might actually clean up these. So you try, see how you can get on RCSB and find the systems. I might send you a PDB where I have corrected all the issues, and where you make these changes and you save it, it will work fine. So I might have to work that on my Linux system. Okay, so we'll see. I maybe just want to check, is it creating? No, it's not creating the PDBQT. But that is a procedure you will follow for that. Okay. I won't troubleshoot it now. Okay. But that is the procedure that you will have to follow. Okay, so what I might do is I would like you to go to the RCSB and to get those structures, but to at least have a look at them. You can open them in Discovery Studio, for instance, but I will make sure that we have available to us some clean structures that we can work with. Okay. That is the procedure we're going to work, and you will then file save as, and when all goes well, you'll be able to save it as a PDQT and it will work well. Okay, I'll troubleshoot that and get back to you on that. Okay, but there was one final thing that I wanted to show you while we've got time, is that I had a query yesterday about working with zinc. And when you go to zinc, you might do a search for some compounds. So here's a particular compound that you might search for. And if I can get this compound to be correct. Yes, that's correct. There's an acetyl group here. There's an oxygen over here and 2 nitrogens. Okay. If you search all subsets with maybe a substructure search, you'll end up with maybe about 100 structures that you've got to work with from the zinc database. The question is, how on earth could you work with 100 structures? And 100 structures is quite straightforward, because when you download it, you can download it as an SDF file. And that SDF file will contain every single one of those 100 molecules. I'm going to save that file. And it's now saved. And if I just refresh, I think it's saved to downloads. Let's just check where it is. Oh, it's all.sdf is where it's saved. So there we go. So it's all.sdf. So I copy that all.sdf to the cluster. Now, of course, with 100 molecules, I really don't recommend you try and use Gaussian on this. Let's see. If I do ls here on the cluster now, have I copied all.sdf? There, the 100 structures are now in that file, all.sdf. And so I'm going to make a directory called all, and I'm going to move all.sdf to the directory all. And the thing is that that if I put 100 molecules here, it's going to make my root directory really, really messy. So that's why I put in a subdirectory. I've made a directory, and if I change directory, cd to all, and I type ls again, you'll see that all.SDF is over there. Now, we can use Babel to get all 100 molecules out, but please be careful with Babel because we're going to have to make 2 changes to the way we work with Babel. So we do Babel as before. The input is an SDF file, and it's all.SDF. The output would be nice to make it XYZ because we've got so many molecules, we don't really want to work with Gaussian. Output XYZ, and you do molecule, maybe mol.xyz. Okay, but you have to make 2 changes. One is that we might not have hydrogens. I don't know if hydrogens are present on this molecule. So add an extra word. The minus H tells you to add hydrogens to the system, and the minus M tells you to tells Babel to split it into multiple files. So if you do Babel minus ISDF, the input file, the output is XYZ, but add these 2, the minus H and the minus M. It'll add hydrogens to it, make sure that it's fully protonated, that all atoms are present, so that when we do electronic structure calculations, we've got the correct number of electrons, and we do multiple. Then when you press enter, it will extract 100 molecules converted, 100 files output. The first is mol1.xyz. Okay, so if you do ls now, you have now all.SDF. Okay, so the problem then is we would then have to, with the XDB, we'd have to do module add XTB, and we would have to then do XTB from all of them. We'd have to XTB mol1.xyz, and once you've done that, so you'd have to do that for the first one. Okay, and you can see that it's now created the XTB opt, and then of course you've got to convert it because the second XTB will overwrite the XTB opt. So what you would do then is you would do Babel minus IXYZ XTB opt dot XYZ minus O PDB. And that was mol1 that we did, mol1.pdb. Okay, and then you would have to go, I'm going to press up arrow a couple of times, then you would have to do it for mol2, the same thing for mol2, and then you would have to then convert for mol2. So you have to do it 100 times. You would be able to get all 100. Okay, so that's in principle what you have to do. Of course, this terminal I am in is a bash terminal. And so there are commands that you can use. There are commands that you can use that will make it easy, that will tell the terminal to do a particular task 100 times. And if you're really interested with that, drop me an email and I'll tell you exactly. If you tell me what files you've got or what directory in, I can tell you the command to type. It's a loop that will run through, but I don't want to add that to the complication here. Okay, so please, this is what I want you to do, is I would like you to go to RCSB and see if you can at least find those structures. I'm going to troubleshoot why this AutoDoc is giving an issue, and I'll maybe compare it with my other AutoDoc tools to see what's going on. I thought it was confirmations, but it may be more than confirmations. But I will either show you the solution around how to get it to work, or I will send you a cleaned up structure that will make it easier for you to work with. Are there any questions? We've got a couple of minutes remaining.
Prof. Log.
Yes?
I have a question about the write-up.
Yes.
Yes, so what else would you like us to add into the write-up in terms of data or diagrams?
Okay.
And
so what's going to happen is that all these techniques we've got, so what you will have in that write-up is you just need an introduction to this main protease, this COVID-19 main protease. Then we need to speak about the ligands that we've chosen, these 5 ligands. 5 ligands are co-crystallized ligands from RCSB. You'll find that all the structures we've got, and the ones I asked you to draw are the co-crystallized ligands. So you'll need to speak a bit about those. Speak how you prepare the ligands. Do you do, what have you done with them? Have you got any properties of a ligands? Did you do a Gaussian optimization? Are you able to view HOMO, LUMO, etc. of that? You need in the write-up to show me that you can do all of that. Then how do you prepare the protein? Okay. Question I've got is, are you only working with the 5 ligands, or have you managed to find some other ligands to work with? Okay. So that's the kind of thing that'll be in. And in it, it would be, I'm not fussed as to how you have it, but you could have the technique, you could write about the technique you've used and then put your results in. But there should be lots of figures. You need to show exactly what's going on. But ultimately at the end, it's going to have a molecular docking, and we're going to see the poses. We're going to dock ligands to that receptor, and we'll be able to see the poses of a ligands in the receptor.
Okay.
Okay. Yeah, if I can contact some students who did, if we know students who did honors last year, we could make it, maybe ask their permission if I can show you their write-up to give you an idea. Okay. Their write-up was on a different part. So do you know anyone who did honors last year, if they did the modeling course? Who's around? But I don't want to give it to you without their permission. But you can see what's exactly gone into it. Okay. Last year we did the same things, but on a totally different course. But we use different software as well. But at least you'll get an idea of how it's done. Okay. Any other questions? Okay. Right. Please keep an ear out. I'm going to troubleshoot this, and I'll tell you exactly what we need to do in terms of these PDUs. But I want you to be downloading the structures, at least trying it. We might not be able to save it, but follow through the procedures. Make sure you can. You need to get practice in those. Okay.
Wait, Professor.
Yeah, there's another question. Yeah.
Yeah, I said download the structures. How many do we download?
For the protein structures,
Yes.
there are 5 of them. It's in the assessment task. So there's 5 REC is the one code, 5 REY, 5 RFE, 5 RFT, and 6 WMP. There are 5 structures that you can download.
All right.
Other questions? Okay. Right. If you've got questions, you can. Yes.
Can you please help me with the naming of the ligand, the one we have to delete? Does it have a specific name? Because I saw you deleted the DMS, and then how do you know that the other one is the ligand?
Because I've had a thorough look at this protein. But you get a clue. You can get a clue from if you're familiar with amino acid codes. The co-crystallized ligand is normally towards the end, right at the end, before the waters, but we've deleted waters. So it's normally close to the end. But from RCSB, if you go into RCSB and you go down, it will actually show you. So if I just share the screen. Go to RCSB. And you go down, it gives you a little bit of information. So ligands, they're 2 unique. There's T1J, there's its full name. Okay, and you can see that, that's one that we've drawn actually. and I got you to construct it, but it's also present as co-crystallized ligand. But it would be nice to take the one we constructed and redock it to the system and see if we get the same pose. And here's the dimethyl sulfoxide that we have. Okay, have a look at this. So there's a lot in RCSB that you can explore. And so you can explore ligand interactions on RCSB, for example. Okay, any other questions? Okay. Okay, if there are no other questions, then I'll be in contact with you a bit later on once I've troubleshooted. But please try and work your way through what you can.